Welcome to this video in the Atomic Theory unit. This is 3.6, continuing with atoms and electrons. In today's video, we're going to have two parts where we delve even deeper into electrons and light. In part one of our video, topics are going to include electromagnetic radiation and light, wavelength, frequency, and energy, basic light calculations. And then in part two, we're going to talk about the atomic emission spectra of elements and the ground and excited state and how to differentiate between the two of those. If you have not already done so, make sure you have your companion worksheet handy and printed. You're going to need your chemistry notebook to take notes, a calculator, and a periodic table. So without any further ado, let's get cooking. You're probably wondering why I have a slide depicting a fireworks celebration here when I should be doing a lesson in chemistry. Well, the reality is all fireworks displays are rife with a lot of science behind them, especially chemistry. There's chemical reactions, there's electron transitions, and all this cool stuff that is directly responsible for the creation of what you are seeing here. But before I get into all the craziness and talk about how those colors actually get created, I probably need to talk a little bit about light and review some of the concepts that you have learned in your previous science classes. So let's go. So what is light exactly? Well, light is a form of energy, and it is electromagnetic radiation, which from here on out we will probably refer to as EMR. Electromagnetic radiation is not specifically reserved just for light. There are many different types, from radio waves to UV lights to infrared to X-rays, gamma, and of course visible light. They make up the electromagnetic spectrum, and they travel in waves. Here you can see a bunch of the different sizes of the different waves that we have here, from radio waves back all the way to gamma. You can see that some of these are a little longer, some of these are a little more jagged. We're going to talk about what that means as we get further into the video. So more about light. First thing you guys need to know is some vocabulary, and I'm going to introduce you photons. Now, I am not talking about Star Trek here on the right-hand side, where the photon torpedo was the go-to for the Starship Enterprise when it was fighting Romulans or Klingons or Ferengi or whoever the villain might have been in that particular episode. Your photon is your unit of light energy, and essentially what a photon is are tiny particle-like packets of energy that have no mass that make up that light wave. Photons are really cool because they have something called a wave-particle duality. What a wave-particle duality is the fact that they will behave like a photon and like a wave. So let's talk about this. How does a photon behave like a particle? Well, as you can see here, photons can be reflected, right, in a mirror. I'm sure we've all looked in a mirror at some point and seen our image. They can be refracted. We've all seen what happens to light as it travels through a medium or through glass or through water and gets bent. And light can scatter off of things and be dispersed. That makes it just like a particle, similar to if you threw a tennis ball at a wall and watched it ricochet off and react to the impact. Light is also considered like a wave due to the fact that when photons travel, they will have a wavelength, frequency, and a speed, as we see in this example that we are looking at right here. It wouldn't be a lesson on light if I didn't talk about wavelength and frequency, how they are similar, how they are different, and how they are related. Wavelength, which is abbreviated using the symbol lambda, which is this chicken foot that we see here, is the distance between two corresponding or similar or like parts of a wave. And each wave consists of a crest or a peak or a trough, which is the lower part here. And if you're looking to measure wavelength, you have to measure the distance between two identical parts of the wave. Doesn't matter whether it is the crest or the trough. It won't make a difference. Now, your wavelength is a distance unit, so you can have wavelengths that are measured in any unit that will give you distance. You can essentially do nanometers, you could do meters, you could do miles. Doesn't really make a difference. And what's really cool about wavelengths is different wavelengths of light will appear to our eyes as different colors. Let's check this out. Here I have a bunch of colored pencils, and the color that we perceive in the pencil is the color of the light wave that is reflected back towards our eyes. You guys need to memorize this. So red will be approximately, remember this is going to be ish, 700 nanometers, orange 620-ish, yellow 570, green 510, blue 470, indigo 420, and violet will be about 400. Once you get below violet, you get ultraviolet. Once you get above the red, you get infrared. But our eyes only see this tiny small segment of the electromagnetic spectrum called the visible spectrum. Wavelength is different than frequency. Frequency, symbolized by the Greek letter nu, which to me looks like a V, and some people will use the less confusing lowercase f for frequency, is essentially the number of wavelengths that will pass by a fixed point in 1 unit of time. And the unit that we usually use is the second here. So that number of wavelengths that pass that fixed point is called a cycle, and so frequency is measured in cycles per second, or what we see 1 over second. When we get into the calculations, you'll see why we have to have this, and it's really in order to cancel the units. If we look at the light waves that are down here, the red has very low frequency and long wavelength, and the purple here has high frequency and short wavelength. So there is a relationship between wavelength and frequency, and you guessed it, they are inversely proportional. The longer your wavelength, the lower the frequency. The shorter the wavelength, the higher the frequency. We can also correspond frequency to energy, and that is a direct relationship where the higher the frequency, the more energetic your light wave is. So if we think about gamma radiation, that is incredibly energetic and is damaging to your cells. That is a high frequency wave. Here we can now relate wavelength and frequency to color. Purple, or the violet end of the spectrum, is high frequency, short wavelength, whereas the red is long wavelength and lower frequency. So the red waves would be least energetic, the violet waves would be most energetic. And if you think of a dark room where pictures used to get developed back in the day when everyone used film, there would be red light in there. It would provide just enough light that wasn't so energetic that it would expose the film, but it would give you enough light to work by, and that's why it was red. Coming off frequency and wavelength, we probably should introduce the concept of light speed to you. And here you see Han Solo and Chewbacca in the Millennium Falcon from Star Wars, and they are entering hyperspace, otherwise known as light speed. The speed of light is a constant that we have to know, and what's neat is the speed of light in a vacuum for your physics class, which you will probably go to next year or the year after, is 3.0 times 10 to the 8 meters per second. So we are dealing with a rate here because it is a speed, right? So, but in chemistry, because we are dealing with very small things, right? We don't deal with meters, we are going to deal in nanometers, and that constant is going to be 3.0 times 10 to the 17 nanometers per second. Needless to say, it is crazy fast. Otherwise, the Millennium Falcon probably would not have made the Kessel run in under 12 parsecs. Now the math. I bet you did not know that the speed of light is equal to the wavelength of that light multiplied by its frequency. So essentially what we get here is a formula that says C equals lambda F. And here are your variables. Lambda is obviously wavelength, and that is going to be in nanometers for our chemistry class. The frequency is in hertz or cycles per second. And our speed of light, our constant, which will have infinity significant figures, is in nanometers per second. And as we said before, is 3.0 times 10 to the 17 nanometers per second. Obviously, it is algebra, so if we know 2 out of the 3 terms, we can certainly solve for the term that is missing. Check out how we would do a problem using this new formula. Let's say we want to know what the frequency of light is with a wavelength of 450 nanometers. Well, we have to identify our want, which in this case is frequency. We have to identify our given, which is 450 nanometers, and we've got to now substitute with our units. We know that the speed of light is equal to chicken foot times frequency. So here is my speed of light. And here is my wavelength, which I was given. I am solving for my frequency. Now this has 3 significant figures in it. So now we just got to do some algebra and solve for x. And obs, if I come here, I got to isolate my variable. I'm going to divide by 450 nanometers on this side. What I do to one side, I do to the other. 450 nanometers. That is going to cancel this entire side here, except for the frequency. I'm going to be able to cancel my nanometers. And I'm going to do my mathematics. And that would give me a frequency of 6.67 times 10 to the 14 cycles per second, or hertz. And that is the way we solve those. So now it is your turn. Pause the video now, set up the problem, and solve for the frequency of light with a wavelength of 1550 nanometers. Unpause the video when you have an answer. All right, if you did this one correctly, you should have gotten 1.94 times 10 to the 14 cycles per second, or hertz, to 3 significant figures because 1550 has 3 sig figs. Let's try another. Determine the wavelength of light in nanometers that has a frequency of 8.3 times 10 to the 14 hertz. Pause the video now and then unpause when you have an answer. All right, if you did this one correctly, here is your setup here. It should be the speed of light equals wavelength times your frequency. And when you solve for x, we should get a wavelength of 360 nanometers to 2 significant figures because I had 2 significant figures right here. Not so bad. Let's try one more. Now we're going to calculate the wavelength of light in nanometers with a frequency of 4.60 times 10 to the 14. And I'm even going a little more crazy. What color is the light? Pause the video now and then unpause when you have answers. All right, if you did this one correctly, here's your setup that you have here. When we solve for x, we should get 652 nanometers. So let's now look over here. 652 nanometers. This is 620, 640, 660, 680. So 650 is somewhere here. What color does that look like? That is orange light. And that is how we do simple light calculations. When you get to AP Chem, they will add a little piece to this where you are determining the energy of a photon. If you're interested in that, I could certainly teach it to you. But for now, let's just stick to these light calculations. Now that we are done with the math, let's jump into part 2 of this video and look at how atoms reach something called the excited state and emit light, which is what we see during those awesome fireworks displays during 4th of July. The secret is you got to add energy. Before we get to the particulars of that, we've got to talk about the ground versus excited state of an atom. Now, you may remember from a previous video that the ground state is essentially the lowest energy state and most stable state of any atom, and it has to do with the electrons and where exactly they are located. Remember, when you're grounded, in order to identify the ground state of an electron configuration, your atom would have had to have distributed electrons that agree with the 3 rules of filling, and that is the Aufbau principle, the Hund rule, and the Pauli exclusion principle. If you didn't cover that in your class, don't worry. All we would have to do is check the electron configurations on the periodic table. And if you were given something that had 11 electrons, we would go to sodium. And if it matched 281, you would know that that is a ground state electron configuration. If it had 17 electrons and it said 287 in that order, you would know you had a ground state electron configuration for chlorine. So as long as they match what's written on the periodic table, they were filled according to the rules of Philly, and they are in the lowest energy state possible, which is the ground state. Well, the excited state is the opposite of the ground state. The excited state is an energy state above the ground state. And how did it get there? Well, electrons get energized, and they now occupy higher energy levels than they normally would. So any one of these elements that you see here would not have an electron configuration that matches this if it was excited. Check out this example. Here I have 272. Let's add up the electrons. Well, I got 11 electrons here. 11 electrons tells me I have, you guessed it, sodium. Well, sodium's ground state electron configuration is 281. That must mean this is an excited electron configuration. It means energy must have put in, and one of these electrons jumped up into an energy level where it should not technically be. Let's check this out. 2 and 8 is 10, 16 is 26, and 12 is 38. Does 38 electrons, which corresponds to strontium, match this electron configuration here? Heck no. Here it says 18, 8, and 2. Here I have 16, 8, and 4. So this is also excited. And obviously here I have 17 electrons. 287 is the ground state electron configuration for 17 electrons. Here it says 278. That means one of these electrons jumped up a ring where it shouldn't have. This is also excited. So identifying the excited state is not that difficult. This is also the case for any SPDF electron configurations. Just throwing it out there. Here we have 1s2, 2s2, 2p5, 3s2. This is an excited state electron configuration for sodium. Well, how do I know that? Well, we know that because if we add up all the electrons, 2 plus 2 plus 5 plus 2, which are all the superscripts we see here, we get 11 electrons. Now, the idea is, well, what's the actual electron configuration for sodium? Well, if we look at our periodic table, we know it's 1s2, 2s2, 2p6, 3s1. This is the electron configuration according to the rules of filling, and it looks like to me there was a 2p electron that jumped up to the 3s, and that's what makes this an excited state. So you try this one. Is this a ground or excited state electron configuration? What is the identity of this element? Pause the video now and then unpause when you have an answer. Well, if you did this one correctly, you would have to add up the electrons. So let's see, we got 2, 4, 6 is 10, 11, we got 17. So in order to figure out whether this is excited or ground, we got to write an electron configuration for 17. Go to your periodic table and look at chlorine. Chlorine's electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p5. And so I see here we have had a jump from the 3s to the 3p. This is indeed an excited state electron configuration, and it is chlorine that was excited. So before I give you guys a summary on how to get your electrons excited and how they actually create light, I wanted to give you a visual that you could look at and harken back to as you were writing down the summary. So the way this works is pretty simple. In order for an atom to have electrons that are excited, they have to absorb energy. So we have absorption of energy, and that's going to be in the form of heat or light. So energy comes in, you know, your electrons are on the outside of the atom, and they are the first to get hit by that. Those electrons that are in lower energy levels then jump into higher energy levels. So here we have the first energy level, and here we have the electron that now jumped into the third energy level. Once that electron absorbs that energy and jumps into the third level, it is now considered excited. When it is excited, it is unstable. Because it's unstable, this electron will then release the energy that it absorbed as it is returning to the ground state, which is here, its original energy level that it was in. This is the energy that it had absorbed that it is now releasing, and it is releasing energy in the form of a photon. The colors that we would see in the fireworks is the release of that energy as that electron is returning to the ground state. If you didn't catch all of that, here is a summary. So pause the video now, copy the summary, and then unpause when you got it all in your notes. The release of the photons of light by those electrons of an excited atom is known as the atomic emission spectrum. And that is essentially what you are seeing when fireworks are exploding in the sky and you're getting all those colors. Depending on what the elements are, the light we see is sometimes a combination of different colors. And here you can see your chemistry of fireworks where they're giving you all the colors that you see exploding in the sky. And many of them are mixtures of a bunch of different colors and a bunch of different metal salts. It's not all about fireworks in this lesson. There is some relevance to chemistry, and the relevance is here. Elements with energized or excited electrons will emit unique light waves at very specific wavelengths. So the wavelengths that are released by copper are not going to be what is released by potassium or lithium or strontium or titanium, etc. And because the light waves emitted by each element are unique, we can use those emissions to tell different elements apart and sometimes identify the identity of elements. Let's do an example. Imagine I said to you, are these two atomic emission spectra the same, and are the two elements creating them the same? Well, to the naked eye, I sure as heck am seeing an orange to red flame that's being emitted, so they must be the same element, right? But my naked eye is not good enough to really discern all the different wavelengths that are being emitted by these elements that are releasing light. So what we have to do is look at what's called spectral line patterns. Spectral line patterns are examined by using something called a spectroscope, and you may have used this in other science classes before, where it takes the light and will break it into component wavelengths to create lines. What it looks like is this. So our first flame that's here has this spectral line pattern. Now, in there, it looks like there's some blue light, some green, some yellow, as well as the orange and the red. We would never have seen that with the naked eye, but the spectroscope will break up that light and show you this. Here's our second. Now, to me, it looks like these are two completely different elements because the spectral line patterns are different. This bottom one here is missing the green and the yellow. So I can say unequivocally that the identity of the two atoms that are being excited here, or the two elements that are being excited here, is different. The uniqueness of our spectral lines not only allow us to tell two different elements apart, but can also be used to determine the identity of atoms. Check out this example here. In this example below, I have 4 spectral line patterns: lithium, hydrogen, helium, and sodium. I also have an unknown, which they are telling me is a mixture of these 4. So I can now use the spectral line patterns to discern what the components of the mixture are. And the way I do this is I look to see which one of these elements match the pattern in the unknown. I do that by really just marking the whole thing up. I can see that the mixture, which is down here, has components of helium because the spectral line patterns all match that are here, and also has components of hydrogen because they also have these components that match. I can rule out sodium because sodium has a spectral line pattern here that this mixture does not have. I can also rule out lithium because lithium is missing these spectral line patterns. So it is almost like doing some sleuthing using DNA, except we are using light. Final thing I want to talk to before I let you go is that the energy of the light wave that gets emitted in the atomic emission spectra is based on the different separations between the ground and excited state. So essentially, the distances that the electron travel are directly proportional to the energy of the light wave that is emitted in the atomic emission spectrum. The way it works is the larger the transition, the higher the frequency of the light that's emitted. So remember, the blue end of the spectrum and purple end of the spectrum is high energy. High energy means it was probably a very large transition, like 1 to 6 or maybe, 1 to 5, whereas red light is a small transition, maybe 1 to 2, 3 to 4, etc. If you look at this picture, which is here, it captures it really nicely, that if you saw an emission that had a wavelength of 410 nanometers, you could correspond essentially to being in the 6th principal energy level, which is here in the excited state, and that dropping all the way down to the 2nd. Whereas maybe red light that got emitted with a wavelength of 656 nanometers maybe only was excited in the 3rd energy level and then dropped back down to the 2nd. So it was not a high energy light wave because it was not a large transition. So that is it for me. If you guys found any of this stuff difficult or have any burning questions, please make sure that you bring them to the Burning Questions segment during our next session. It has been a pleasure taking you through the final part of our Atomic Theory and Electrons chapter. I'm going to see you guys in class. Peace out.
That's all, folks.